In, as you know, in many parts of India, we supply water from groundwater itself. And then how to keep that water safe, prevent from any contamination. And then the role will be how we can recharge, even though we are changing large pervious area into unpervious area. That means we are reducing the percolation, we are reducing the amount that water can percolate in the ground. That means the water level is changing, the availability of water. Regulating the use of groundwater. I'm not sure how much the regulation is playing a role in managing how much individuals can extract water from ground for maybe the agriculture purpose, for any other purpose. Then how we can balance the input and output. These are some of the issues which I think are faced over here. But in Australia, our situation is a little bit different. The water is saline. Salinity is very, very high. We can't use it for drinking purposes, for any other purposes. Until unless it is, we put RO or reverse osmosis process on any desalination process. So the state, mostly all the bigger cities, they have quite big desalination plant for meeting the water requirement. And the cost associated greenhouse gas emissions, they such a huge quantity that, but it is an insurance policy too. If you don't have other sources to meet the water requirement, where will it go? That's why most of the politicians in those states, they put money in developing desalination plants so that they can provide drinking water sources for their residents. So on one side it is insurance policy, but now the situation has changed. We have sufficient water, and we are just operating them because we can't close, we can turn on and off desalination plants. You have to run them at a minimal level. So keep them running. So I think regulation should be there. How we should enforce urban development for agencies, that their planning should be such that still there should be some recharge structures within the urban area so that the depletion aspect can be minimized. But application, I think in India, we are using a lot of groundwater for not only for urban areas, for irrigation purposes too. But how much we are considering about recharging of groundwater? You are working in that area, maybe you can comment. I'm away from the country for many, many years, so I'm just hearing from experts about it. I think you can provide some comment on that. What is happening with the groundwater issues in India? The recharge is again a question mark.
The recharge everywhere is not possible. I already hinted on day one. Because, for example, in my state, soil depth is very, very shallow. We have maybe above the bedrock, if you take mostly unconfined aquifers, and you have confined aquifers, but then drop from confined aquifers, I say, is not that high. Then every house, almost 80% of the houses, I should say, have their own well.
Yeah.
And it's mostly unconfined aquifers, and that depth is roughly about, at the most, 10 to 20 meters,
yeah,
even less. And during this monsoon, when you have rains, maybe 3-4 days if it rains very heavily, water table is almost near the ground.
Near the ground, yeah.
And let's say a week or so after the rain, it drastically falls.
Yeah.
And because the topographical gradient is very steep, then means it's a very narrow strip of land. On one side Western Ghats, on the other side it's ocean.
Yeah.
So across these state if you take topographical gradient is very steep. And hydraulic gradient almost will follow suit. So because of the steep hydraulic gradients and the generally porous nature of the soil, whatever you inject,
Yeah.
that will
run away.
run away.
Yeah.
So there's a limit to what you can do. And you cannot maintain very high water table conditions like that. So what generally in the magnetic plains, even in peninsular India where soils are very weak.
So because of the high water table, and you said it comes almost on the surface when it is heavy rainfall, are you changing any design aspect of foundations of homes?
See, typically, a single story house with the type doesn't matter because it may be little below the ground, but then we don't have the soils are generally. But then if you go to say areas like Cochin, etc., where water tables are high, it's mostly clay soil. So generally, they have even for maybe 2-story houses, they do piling.
Piling.
Otherwise, they do some type of stabilization and all.
Yes. But single story, it doesn't matter much. Yeah.
But then sometimes you have the differences in old houses and all, you see cracks in the walls and all.
Yeah.
Differences in cement and all.
So most of the foundation for single homes, they are footings. Is that right?
Normally
Or they put a
it's,
slab foundation.
not slab,
Normal
combination type of
Yeah.
footing foundation.
In Australia nowadays, they are putting basically the slabs because of drought. Yeah, because of these settlement issues. Even then, there are cracks within a very short period of time. Okay, then I think.
In Delhi, to some extent, they have created some structures near the flyovers for artificial recharge. The stormwater is there.
Yeah.
So near Dholapur, so they have irrigation kits and then water. Then somewhere they have constructed in Lodhighat and other trenches also.
Trenches also.
To some extent, particularly in South Delhi, where the groundwater level is deep. So some limited investment like in GNU. Somewhere they have constructed the artificial discharge structures, but not in not Delhi because water level is already high. But like in our campus, there was a problem of this every time during rains, 5-10 years ago, I think 7-8 years ago, it used to be flooded all the time during rains. Just like no stormwater used to be there outside the roads, some water used to be stagnated. So then we thought that there is some problem. Already this problem of the high water table. But that was not because of that. It was because of this poor drainage system. So a survey was undertaken in our campus. Now the problem has been sorted out. So this proper drainage, the underground drainage, somewhere the slope and the gradient and the design was not right. It was basically a technical problem.
Maybe the maintenance issues too.
Because in Delhi, the last flood was in 1978.
Yeah.
In 1978, after that, we have not witnessed a large-scale flooding in urban areas, especially after the construction of Outer Ring Road. After that, what happened during that time, even the North Delhi area where I stayed, the level of the soil drainage and the water comes out from the walls, and some people have reconstructed and they've rebuilt foundations with soil substructures, and then the problem is sorted out. It's still in some old areas the problem is. So the effect of that last flood, 1978, still can be reflected in some of the governments.
Yeah. So there is a lot to do in that area.
So I think he's right. You are all engineers. In most of the structures, most of the problems are because of the faulty engineering design.
Yeah.
This is why we.
Yeah, you are right.
I agree with Professor.
Yeah.
Sir, most of the problems are with faulty engineering design, I would say. Debris clogging, and this is fine. Like in Delhi, I just cited the example of my own campus. It used to be flood all the time. और पूरा hostel में पूरा flood हुआ. The people had to go need and this water. Now the problem has been sorted out because we saw that this proper gradient, each and every inch of the land has to be measured accurately and scientifically. वही बात है contractor को आप दे दो वो क्या कर रहे हैं क्या नहीं कर रहे हैं उसको supervision.
There are two things. One is what you're talking about the design issue.
The other one is the flooding.
There is another issue with the construction aspect of it. Sometimes you will see the construction is not as per the design. So there is this link between the design and the construction. So those who are constructing, they either are not technically capable to look into the technical aspect of the design properly, and that is another part. So there are a combination of factors.
Surface drainage also matters a lot.
Yes.
Subsurface, the soil, that is important.
So keep waiting for us to start.
Yeah, no problem. Yeah, hello. Yes, yes, yeah. I was just waiting so that I see a good discussion which is happening. So I thought I'll just listen to it. Yeah. I'll just start. Okay, so I'll share my screen back again. And now we'll see a bit more practical aspects. So first thing, before going into practical aspects, I'll show you some slide where we'll see what are the quality checks. As you know, stormwater network for any city or any stormwater network, it has a lot of pipes, a lot of inlets, so there are a lot of data. So first, the major aspect for any designer or modeler is to check the quality of the data. So every software has its own, some software has its own quality checks and some softwares don't. So I'll just show you what the quality checks which Tuflo has, so that you can use it when you're doing that. I'll just show you, share the presentation slide. Okay, yeah, you can see my screen right now.
Yeah, we can see.
Yes, yeah. So as I said, we'll see the quality control kind of demonstration. So so this is one area where you'll have 10,000 pipes and inlets and manholes. So when these cases, you need to have some quality checks. So you can, instead of doing manually seeing what is the data set, how it has one by one, it takes a lot of time. So we are using some automations in Python tools, which was developed by Tuflo team for quality checks. So these are the inlets. So as I say, inlet means it is the point where the overland flow will be transferred to the underground. So that is the inlet. So these are the points at the inlets and manholes. And as you see, any data will have, most of the data sets will have varied quality. You can see the connectivity of the pipe to this main pipe. It is not connected. You can see it is unsnapped. So the snapping issues will create a lot of problems. So you need to rectify those. So it's not possible always to go one by one and check all these. So we have some tools within Tuflo. I'll explain you. And the other most common is the object digitized direction. You can see this is a pipe network, and you can see this one pipe which is in red color. It is digitized in opposite manner too. So this is the pipe flow, pipe direction flow, and this is digitized in opposite way from downstream to upstream like this. So this is not correct. So it has to be in the other direction. So these direction checks also we can do in Tuflo, and some of them are the inverts. So you can see that this is a pipe long section. So you can see obviously that this pipe is the odd man out. So the invert of this is not properly aligned with either of the upstream and downstream. It has to be in the opposite direction essentially. So these kind of checks we can do. So yeah, so these are the two various things, and you can see this also. It is not fit, even though it might be correct, but it is not exactly. It just show you some of the checks which we'll do. So it's not even though the inverts are okay, but the size you can see the upstream and downstream is a bit different. So those things, and so as any modeling or any design, whatever the input data you're giving in, that will be the quality of your output results. So always you need to make sure your data which is going in is correct. So let it be the digital terrain elevation data sets, or the land use land cover, or the pipe data sets, or the whatever is the inlets which you're having. So all these outcomes will depend, the outcomes of these will depend on the outcomes of your modeling results and what applications it is being used for. Okay, now it's will be a bit of hands-on session kind of thing. So you won't be doing it manually. You won't be doing it with you, but I'll show you one by one what we are doing. So one thing is, this is a QGIS workspace. So I think most of you already knows about GIS or QGIS. So QGIS is a free source software which is widely popular, which has a lot of user base, a lot of free plugins. So one plugin, as I said, was QGIS 2Flow plugin. So you can, I think you can install that. So if you haven't installed, go to plugins and manage plugins. So there, once you have there, you'll be having the 2Flow plugin. So once you click on the manage install plugins, you'll be getting this dialog box. And now just type in 2Flow here. So this is a 2Flow plugin, and click install. So I already have this plugin, but for you, it will be having as install plugin. So you'll be installing that. And now the next is, once you install that, once you go to plugins, there's a 2Flow menu. So in that, these are all the 2Flow options which are available, which you can use it for your model build. And today, what we'll be using is 1D integrity tool. This is a tool for urban stormwater networks, or for whatever is the checks what I told previously. So for all these checks, we use 1D integrity tool. So this is the tool developed in Python. So even the Python code is freely available for this tool. So if anyone want to modify that, you who are good in programming, you can use that to modify based on your requirement. So these are all our different Python tools developed by the 2Flow team in an open source QGIS platform. So if someone is very good at GIS, they can use their skills in GIS as well as integrating with with 2Flow. So I'll show you what is there in the integrity tool. So in the integrity tool, we'll be doing all these checks. One is snapping, pipe direction, network continuity, and flow trace. So we'll be seeing what does all of these contain. So let's take one example. I'm not sure which area this is, somewhere I guess in Australia only. So this is pipe network. Now we'll be doing a demonstration of the snapping issue. So for that, let's go into the 1D integrity tool, plugins, 2Flow, and integrity tool. So now this is the integrity tool which you'll be getting. So you'll be having input network lines you need to give here. What is the shape file? So 2Flow is always dependent upon shape GIS files. So whatever is your pipe network as shape file, you'll be giving it this as input, and this is the network points. So whatever is the input pits, or whatever is the inlets, you'll be giving it to, one is the lines and the other is the points. So once you have given those two, so that is one input which you have to give. So the input layers, you just have to specify and click this plus button to add that into the tool. And there's another section which is called as QA QC functions. So this has all the functions. You can see the snapping, pipe direction, continuity, flow trace, and channel ID. So all these functions, we'll be using it based on our inputs. Whatever we give the inputs, it will process it into these functions, basically we call it. So we'll look into that now. So now this is the pipe network. So just adding that pipe network, and we are adding the points, which is inlets. Now we'll be going to a snapping button. So this is a snapping tool check, which we'll be using it. And just click on run. So now you can see these are the points which 2Flow finds that it is having errors with snapping. So let's see what are the errors which it has.
Excuse me, Rishi.
Yes, sir. Yeah.
What is the physical meaning, so that we all are clear about the snapping?
Okay, yes. So snapping so what I'm saying about snapping is, if any pipe network is there, so one pipe connects to the other pipe, but in GIS it's not connected basically. There's some gap. You can see the gap here. Even though from zoomed out, it is showing as connected, you can see that it is not snapped properly. So that is the connection basically.
So basically,
the pipe should be connected.
It is the connectivity issue.
Yeah. It is a connectivity issue, definitely correct.
Okay.
That's what's.
Error in
Yeah.
Error in digitization.
Error in digitization.
Yes, yeah, correct. So that is correct. So, in few cases, by mistake we don't snap it because there are a lot of pipes and it might get here and there. So it will just show you the errors which it has. So now, example, this is the one connectivity like snapping issue. So it's not snapped. Now what we'll do, it will, if you have this option tick as auto snap, so whichever is like this within some radius, so you can give some specific radius. So within that radius, it will snap all the pipes which are within that. So say if you give small radius as 2 meters or 5 meters, so within this such radius, it will snap all the pipes into one junction, basically. So just click on auto snap and run button. Run. So it'll create a new. You can see this is the new file. This is the new layer which it creates with the snap option. I'll just show you that. Yeah. So now you can see it is connected now. It will automatically create a new layer with the connected ones, basically.
Okay.
Yeah. So now it is all connected now. That is what.
So it is
So this
connected, but how is going to take into consideration the direction of flow?
Yeah, so the direction is again, the next one is the next tool. So when we're drawing the pipe, so we have to connect that, means we have to take upstream and start to draw this downstream. So just try to direct in that direction.
Okay.
So from upstream to downstream, we can, so what we are giving, it will take, but there is a check for pipe direction as well. I'll tell you the next tool. This is about snapping. So now I'll tell about pipe direction. In the same, the next one is pipe direction. So what they have some, I think you can check the pipe direction and will connect based on the selected rules. So once if you have, there are two rules here. One is the based on the pipe direction continuity. So I'll just tell what it will contain. So with an example, one second. So I'll just run it and show you what it is. So once I run it, it will show some errors. It'll show some layer which will have some errors. So this is the layer which has output as the output of whatever we ran. So these are the 3 points which are having pipe direction issues. So if we just zoom into one area, so yeah, so this is the area. Now we can see here this this is all along this direction, but this was digitized in opposite direction. So it will show you the label as has been reversed. So whatever we want, it will we have to reverse this pipe direction in this direction. So it will show you which are the places which we have to reverse the direction. So this is based on like continuity. So if the flow, all the pipes in this direction, so the continuity has to be in this way. But this pipe was digitized in opposite direction. So it will change it to the continuity, whatever it is, and it will show us the output. Means it will give us the modified layer as well, which we can use for further analysis. So it will, one thing is it will identify the error and it will also correct the error. So that is the useful feature of this. So in most cases, like most softwares, they'll just identify the error, but it doesn't automatically correct it. So this is also one good feature in TwoFlow. It'll in the tool, we can connect it as well. Yes, you have any questions here? So we just have to, you can maybe read through the documentation for this. So it has some description here.
Please feel free to ask any question if anyone has. Okay.
Sometimes we need to manually correct these. What about, as you said, that it auto corrects? But,
Yes.
but in many other GI software, sometimes we need to manually correct.
Manually
What is
correct.
the
Yes, ma'am.
reliability of this?
Yes, yeah. So yeah, it is actually based on some rules. So it will basically show you what areas it is correcting it. So this black dot, it is whatever is output, black dot. These are the areas which it is auto correcting it. So if you want to change some areas which you want to manually correct it, manually equip it, so you have to go on that and keep it as it is. So we have option for not auto correcting as well. Just show the errors which it is located. If you want to autocorrect, just click that autocorrect option and it will autocorrect. So we have the option for manual as well as autocorrect.
You can continue now. Thank you.
Yes, yeah. So yeah, so I'll just show you the next part. So this is on pipe direction. I go to network continuity. So this is the one tool which has all the checks for network continuity. So when I say continuity, some of the rules for continuity in the pipe network is the flow area check. So check the downstream of the flow area does not increase. So as it does not decrease. Sorry. So as logically, if you go from upstream to downstream, the flow area or the size of the pipes will generally increase. In few cases, it will decrease, but it will just show you the check kind of thing. So if something is wrong, usually if say suppose if going from 10 meters to 20 meters, then that is logically okay. But if the 10 meters goes to 5 meters, that might not be, it'll just give you a check kind of thing. So this is the flow area check. If you want to have that, just take this and invert check. So if there's any adverse gradients, so inverts usually from upstream to downstream, the gradients or the invert should be reducing. But if it's not reducing, if it's having kind of adverse slope means it is negative slope. So that is where it will give you this check. It will not correct it. It will just give you the checks for us to see is it correct or not. And there's an angle check as well. So if there's a connectivity, means suppose there are two pipes connecting, and the angle of those two pipes are greater than 70 degrees, or sorry, less than 70 degrees. So it is kind of too obtuse, I mean acute angle. So which might not be. It'll just show you the check kind of thing. So this is angle check, and this is a ground cover check. So ground cover means whatever is inlet from the ground to the pipe. So that is the manhole depth. So that manhole depth, if it is usually as per the general recommendation, there should be more than 0.5 meters for the depth of the manhole. If it is less than that, it will just show you the ground cover check. Give whatever you want the default for that, 0.5 or 1 meter or 2 meters. So it will show you wherever is the location which is having less than that ground cover. So this is all about network continuity. It will not do any correction. It will just show you if that is correct or not from the general recommended practice of network models. So this is one, and the next one is yeah, I'll show you about flow trace. So this is about flow trace, where apart from whatever I told earlier about flow area check, cover check, and other things. So here this is very useful in terms of generate long section plots. So when just click on this and select um, any outflow location. So this is the final outflow location. So just click on that. So this will select whichever is upstream of this outflow location. So all the upstream channels it will select, and apart from it, it will create a long section plot of all the upstream areas. So it has different paths. I'll just expand this. So here it has different paths. You can see there are different paths. So that is, each path will have its own long section. And I'll just show you what. So suppose this path one, and select path in the workspace. If we click it, it will show you one second. Okay, just see if this is the different paths, part 2, part 3, part 4. So one path, if you see here, it has some check here. That is, the check is area decrease. So if you see here, all the other pipes are small or one area, and this is the higher area. So just show you the check. So that check also we can see in the long section plot. And also there's select path in workspace. If you select the path in workspace, it'll show you that path. So as you see, this is one outlet. So this is one of the flow path for this outlet pipe. So in similar way, there are different paths, around maybe 20 paths in this model. So this one outlet will have different paths. So this is one path, two path, three paths. So there'll be various paths within that. So that is what this flow trace is very useful in checking how is the long section view of that for each path, and we can visualize that graphically as well. So this is based on flow trace. So and also we can label the network. So the pipe names also can be labeled based on each of these. I'll just show you. So you can see these are each of the pipe names. So those pipe names can be labeled in the viewer. So in similar way, you can see all the different pipe networks with different flow paths. The orange line, what you see is the ground cover level. So the water is the ground level, and you can see one check which shows that the ground level here, the pipe lays higher than the ground level, which is not, which might not be correct. So that we have to check why it is going beyond the ground level. This is the ground level of the terrain topography. So this is all about flow trace. So say suppose for any other long section also we can visualize in the similar manner. So it'll just take some time to calculate, but I think you have understood whatever what I wanted to. So say for this outlet, this is all the upstream sections of this for this outlet point. So this outlet might be for different one, but this is for separate one. So now say suppose we will calculate for this outlet. So all the upstream of that outlet it will select, and we can see one by one what it is. Okay, so now we'll see a bit. Yeah.
Sir, I have, which layer is that in background, sir? It is satellite image or digital animation?
No, it is a digital imagery, DTM. So we just have added a hill shade for that to visualize it a bit
How
directly.
we are getting elevation or gradient in that information? Means it is surveyed or we are getting the information of elevation by extracting in that from that elevation model.
Okay,
Yes.
okay. Means you're saying the DTM which is having some protrusion, means kind of 3D effect. You're saying, yeah. So in QGIS we can the DTM whatever it is there. If you add that hill shade, it is called as. So we can visualize that in kind of a three-dimensional topography. So DTM has the topography values. So that will once we add that hill shade, it will have this three-dimensional effect.
Because in public domain, it's freely available only 30-meter resolution. So.
Okay, yeah. So this one it has a like 1 meter resolution. DTM is 1 or 5 meters, I think. I'm not sure. So it is around 1 meter. It's a quite a finer resolution DTM.
So which dam you are using, sir?
Yeah, this is like LiDAR based LiDAR data.
LiDAR.
Yeah, LiDAR. So it's around 1 meter, I think. 1 meter resolution or 5 meters. I think. So we'll quickly go over some of the results. How to so once we run the model, TrueFlow will give you a shapefile based results as well as CSV, so that anyone can use without a license as well. So they can just load in the results, and so there's something called as TrueFlow Viewer. So which is where we'll use to visualize our results. So this is again a Python plugin which is developed by the TrueFlow team. So we'll just visualize some of the results which we have got. So I'll just load in some of the results. Yeah, so so this is the one of few of the results. You can see the flood extent of that. Okay, so one of the results was this shape file, which is called as 1D_CCA_L. So this is for as a summary for pipe capacity, whatever is the flows and maximum flows, what is the time duration, and what is the percentage of maximum flow. So if you see an attribute table, you can see what is the area max, what is the percent P time full means percentage time to full, percentage full maximum, and what is the duration full and 10% and surcharge. So these are the different options which we have. So basically summary of the pipe network. So one good thing to will see is that we can symbolize that based on an area. So I'll just show you. 1 second. Okay, so based on percentage full maximum. So what is the maximum pipe capacity which is carrying? So this is the percentages, 0, 15%. We'll just categorize that in QGIS, and now you can see which are the ones. So the red ones are the, like having higher full capacity, and the blue ones are lesser capacity. So you can just visualize that which are the areas which is having full capacity. So if you see here, these two pipes are having red color means high capacity, means it is fully flowing full capacity. In between is the orange one, which is having a lesser capacity. So we have to see if that is correct or not. So those are the things which we can visualize. And in similar way, we can even have for time series. So there's option for time series. So if you just select on any one of the line for pipe network, so just say select your time, selecting the time series. We want to know the time series of pipe. So once you select the flow within that, and now we'll select any pipe network you can select. Just select that pipe. Just a minute. So yeah, so this is the flow within that pipe network across time. You can select any number of pipes, so that will be giving you the time series for each of the pipe flows. And there's another option for cross section or long profile. So if you want to see the long profile view of that. So you can use that cross-section long profile tool. So here, so it says, like for example, you want to have a long section plot of any between these two lines, which are selected. So you can plot this long section profile, and then you can plot the water level. What is the water level within that? I'll show you that next. It should. Yes, so you can plot this. You can see this is the pipe, and you can plot whatever is the time series within that pipe, as well as what is the flow downstream of the pipe. You can see these two pipes. The upstream is high, but the downstream it is not taking any flow at all. So it's not. It's just surcharging from this pit area. So that is why the flow is adverse. Means it's coming outside the inlet. So that's why it's coming as negative flows from the inlet. So this is where we have to understand and see. There is also plot for option for maximum and minimum flows. So we can see just plot it based on the flows, 1D MMQ. So we can plot which are having higher flows, which are having lesser flows based on the symbology given here. So I think I'll quickly go over all this. So this is the example for that one MMQ. What is a Qmax, Q peak, time to peak? So based on these, we can symbolize in our QGIS. And the other part is plot. So with the plot, I'll show you a few things. Okay, so these are all about the long section plots. I'll show you. Okay, I'll show you in the example probably. So here now, so one thing is we have to modeling it. Once we have modeled it, we have to use the calibration data. So usually the calibration data might not be available. So we have to go for the council for the stormwater hotspot register and see what is the documented water levels and other aspects. Or in India also we have some river gauges, or we know what are the areas which gets flooded. So once we build the model, you have to calibrate the model against it. And as I said, the effort which we invest on quality checking data inputs and preliminary results after simulation is kind of a very good time spent. So because it's not like wasting time, it's like we need to make our quality checks of the input data as good as possible so that we can rely on our output data whatever we have. And yeah, so I'll show you, if you had no questions, I'll show you the real-time example in my QGIS workspace.
Rishi, one question which I will have is that
Yes, okay, yes, sir.
in case of some manholes overflowing, that means the capacity of the carrying capacity of the pipes is limited.
Yes, sir.
Can we think of putting some detention ponds in the upstream so that we can minimize the flow in the pipes without enhancing the capacity of the pipes, because that can be more expensive. So is that possible using the software?
Yes, so so when you say any different detention ponds, or even we can even divert some of the flows in the upstream. So when you say ponds, we can so there's a capacity for infiltration. So all the detention ponds will have higher infiltration rate. So those infiltration rate we can incorporate in that area, so that all the flows will get infiltrated than going into the inlet pipes. So we'll avoid that, and we'll have a higher infiltration rate in upstream area. Or even we can control the Manning's roughness. So we'll have a higher Manning's roughness so that the water will be ponded over there, and it will have a detention kind of thing. So those aspects we can consider in the modeling part, and basically then it will route the flow in the pipe networks.
Okay. So we can run the model again and see the impact of those infiltration.
Those infiltrations. Yes, yes, yeah. So, so the way we have to do is mostly the infiltration, as well as we can have some diversion channels and all to see what are the impacts of this flood mitigation, basically. I'll show you one example in that. Probably first I'll show you one area. So this is some real-time project. I think it's in like London City. So this is a small river network. Stormwater network, not river network. So this is how it looks. It is not very much. It has hardly around I think few number of pipes around that within 10,000 I think the number of pipes. So these are the pipe networks. If you see, these are the inlets along the road. So this is a road. So it has these are the inlets for the road, and this is how the stormwater pipe networks are connected. And we'll have some invert levels for the pipes. And as so in Tuflo, we just have to give the inlet a location. It'll pick up based on the DTM. So all these invert levels of the, the levels of the inlets is based on the DTM. So if you have on the wrong DTM, it will pick up the wrong inverts of the ground invert. So we should have a proper DTM to pick up these inlets. So we have two things. One is pipe network and one is inlets. So you can see, you might see some of the inlets are not connected to the pipe. But what Tuflo does is within some such distance, these inlets will be connected to the pipe if it is within such distance. Say suppose if you have an inlet placed here where my cursor is, it will not be connected to anything. If it is just within this pipe radius, it will connect that inlet, whatever is coming in, the flow into here, into the pipe network. So this is all the pipes and inlets we have. And so these are the two important inputs. The other input is the DTM. I have the DTM file. It's quite a big file to open. I'll just try to open it if it is. Not sure. Okay. I think it will take time to load the DTM. But this is we have a DTM based on which we'll have a overland flow mechanism. And so these are the files. And apart from that, we have a land use land cover. So for that, might take a bit of time. So we have land use land cover for the Manning's roughness. So based on the Manning's roughness, it will route the flow across the channel. And that's all we are having it here. And you can see we also have a soils value, 2D underscores. This is soils value. So we'll be giving infiltration. Tuflo has the capability to take infiltration based on green ants as well as Hortons and initial and continuing losses. So these are the three common methods where we can take the infiltration. So for if it's green ants, we also have a option to take the USDA soil. So if you specify this is sand, sand, clay, loam, and all those values. So based on the USDA specified hydraulic conductivity, porosity, so it will calculate based on that. Or else we can give our own specified porosity and other aspects in this 2D soil. So we just have to specify the spatially soil parameters and then give the respective details for that. Just a minute, I think I've got this is a satellite image. So you can see these are the Manning's roughness. So Manning's roughness, when I say it is just the values for, say, suppose these are the buildings. Say these are the one of the residential areas. So this will have a higher roughness, and the roads will have different roughness. So that is what I mean about saying the roughness parameters is what we'll be giving it here. So this data is quite extensive. So if I want to show you some of the results, apart from, so this is the Manning's roughness, and also there's a file for just give me a minute. I'll just turn off materials value. I'll show you there's another option for soil. So I'll just say when I said soil, so these are the soils values. If to see what is there in soil, just open the attribute table. So you can see it just has a specific unique ID, but what type of soil it is. So clay to sandy, loam, peat, loam. So all these values, the values for these are there in the reference manual for USDA. So USDA stands for US Department for Agriculture. So they have specified conductivity, porosity, and those things. If you don't want to use those, you can specify your own values, parameters for that, for infiltration. So these are the soils. So it has different soils for this. And we are applying a rainfall as well. So these are the rainfall. We are applying we have to apply different polygons for rainfalls. So all this polygon will have a kind of constant rainfall. But if you have any grids or any other way, we can apply the graded based rainfall, or even if we have rainfall gauges, we can apply the rainfall gauge at locations, and it will interpolate based on Thiessen's polygon value and everything, and let me create a rainfall grid for you to use. So this is all about that, and maybe I'll show you the output. So this is the once you load in the results, so it will have the bed elevation, depth, unit flow, vector velocity, water level, time to peak. So again, there are like lots of outputs it can create. But for now, I've just shown you few outputs. These are the outputs. I'll show you one example here. So if you just specify the depth as max, I'll just show you the result. It, yeah, and you can see this, right? You can have an option to animate like this. So this is a time series slide, and you can animate it like this. So if not, you can also use an option for maximum. So if you just specify this as maximum, you'll have the maximum depths. You can see, like for most of the stormwater network, it will be along the pipe. So because the drainage, it will have the drainage path along the road network. So you can see all the road networks which gets flooded, and what are the depths. So you can have the depth, water level, velocity. You can also turn on the velocity vector like this. So now we can have the velocities. May I just show you? Just expand it and show you. So here for the velocity vectors, you can even specify as 3. And now we can see the velocity vectors, which direction it goes and how it is going. So you can see these are the pits. So now all the overland flow is being directed into these pits. So from these pits, it will be directed into the channels here. So that is one way. And we can also, with this time series and cross-section profile, we can visualize the long section and what is the water level within that. I showed you previous presentations, right? So there you can use all these to plot the time series and cross-section of that. So this is for 1D, and for 2D, we can use these outputs. So this is about the general approach, what we use. So you can see the direction of flow here as well. So this is all about one area in UK. I think this is London, which they have developed for stormwater network for a small area, not all of London. But what I'll show you another example, which I was doing last week. So I was working with IIT Delhi for development of urban stormwater network. So this is almost all of Delhi city. So I'll just show you. Yeah, so this is the Delhi city, and for some most majority part of the Delhi city. So this is the urban stormwater network. And I've got a rainfall data from one of the IMD station for the 2009 floods. So there was a floods in 2009 on July 27th. So there was like kind of a huge floods in Delhi city. So for that, so I had got this Delhi master plan data for this all stormwater network. So in a similar approach, I had built a model in TrueFlow. So what the IIT Delhi was having is they were having a swim model. As I said, swim. So this is a swim model result which we were having it. So it just has the 1D component. It has just the maximum depth, maximum velocity within the pipe networks. But swim doesn't have the capability to link it to the 2D area. So what I've done is I just taken the data, like what is the pipe network data considerations and the DTM, and I built this model. This is the model which I've built, and with this model, I run the TrueFlow model, and this is the depths which I'm getting. So you can see it might not be very much visible because of this. I'll just turn off. So you can see these are the depths in different parts of Delhi city. And also I've just categorized it based on the percentage of flow. If you remember in my previous presentation, the presentation which I showed you, we can categorize it based on the P full max. So what is the percentage full maximum? So 0 to 20%, 20 to 40%, 40 to 60%. So what is the capacity of pipes? You can see all the pipes are almost, red means it is full 80 to 100% capacity. All the pipes are almost running at full capacity except few of these. So we have to go in and see why are these not fully utilized. It might be due to some losses or various cases. So essentially in any flood situation, we have to make sure that we get all the pipes fully utilized because that is what the pipes are meant for. So in a similar way, these are the flood depths, and it has good data sets basically. So this is what now they are trying to use to replicate this for whole of Delhi city and then utilize that for the transport department. So that is what I am working in coordination with them to develop these models. So this is for a Delhi city, which I wanted to show you on this. So I think my video was stuck. Okay. So that is what I wanted to show you. If I can show you the other aspect. So if you want to see any one of the pipe network, what are the flows within that? I think I didn't show you previously. So load results, how to what to load. So if you want to load results, just click on the results. I mean, load results and go to load. I think you'll understand once you start learning the software. So now I'm just loading in the results. Okay, now once the results are loaded, I want to understand what is the flow within this pipe here, whatever is flowing. So, and I'll just turn on the culverts and pipes here, and what is the water level and maximum water level. And now I'll select what is the flow. Suppose I want to know what is the flow through this. So just select on that. It will select all the downstream pipes, whichever is downstream of this. So these are the downstream pipes. So you can see how is the pipe network. And say, suppose if you want to know, just see what is the flow in these two pipes. So you can select these two pipes and this. So this is the flow. And if you want the what is the pit level and what is the inlet levels, there's a inlet level here. Let's see. Yeah, pit ground levels, if any. So you can see these are the ground levels, and this is the water maximum water level. You can play through this like this. Yeah, so you can see it rises till this extent, and how this is how the flood rate occurs. And as I said previously, you can even plot the velocity as well, vector velocity. So this is all about urban stormwater network. As I think, as like Professor Ashok Sharma said, you can suppose if you want to have any pond, detention pond here, so you can specify a region polygon with a higher infiltration or higher Manning's roughness. So all the flood whichever comes here, instead of transferring it into the pipe networks, it can have a detention pond. That is, a detention is water will be detented or stored there with the various areas. So we can let the water stored there. So those things we can do. So this is about a small example of a Delhi stormwater network. This has to be calibrated. A lot of things has to be done. But just as a demonstration, I've built this model. Okay, that is all I think from my presentations. I think I had just gone over time.
Thank you, Rishi. One question: how you're going to calibrate your model?
Yes, sir. Miss, I'm not doing this as a consulting project, but I was just as to demonstrate I've just done this. But for like calibration, what they told me is they have the flooded values. Say this is a 2009 flood event in July 27th. So they have the locations where the flood has occurred during this day. It's kind of a flash floods, just 1 day flood. It was occurred, and on that they have the data which areas are flooded. Say suppose you can see here. I'm not sure. You can see some areas which are very heavily flooded. You can see this area is very much heavily flooded. So based on that, we can calibrate. Only that is only way of calibration, which I think.
So you're doing it your own, or you are involved with the Delhi administration to undertake any study in future?
Yes, sir. No, I'm as of now. It is just a for IIT Delhi. So
Okay.
I'm just trying to. They have purchases software, so I'm just trying to demonstrate a small area for them.
Right.
But they are working definitely with the Delhi Metropolitan Authority for this, as you said, whatever is the urban planning. So maybe I'm in future and I would involve with IIT Delhi to do this planning as well.
Right.
I have two questions.
Yes, absolutely. Go ahead.
Yes.
Sir, I have two questions.
Yeah.
The first
Okay,
one
yes.
is that we have used this Manning coefficient, right? So that
Manning's
Manning
roughness.
coefficient was particularly on the basis of type of soil based on the elevacy cover. Right,
Yes.
sir?
Okay. Yes. No, actually, the Manning's roughness is not based on the soil. So it is for the land, like say buildings or roads.
Right,
so if
sir.
you want to take infiltration, there's a soils capability. So like hydraulic conductivity or porosity and all can be taken in the soils. But this is for land use land cover. Yeah, that is you're correct, but not for soils exactly. You can say.
Okay. So my question is that is it that we are taking the sediment-free water into the drainage system, or there is an opportunity that we can take the sediment-laden water also?
Okay, yeah. So when you're saying sediment water, we can the only way where we can take in two flow classic is based on blockages. So we can give some blockages for the pipes, say as a percentage, but not as a full sediment transport model, like how we do in rivers, right? Sediment transport. It's not
Exactly.
exactly like that. Yeah, but it's not exactly as the sediment transport. So for sediment transport, we have another module for two flow FE that is for river morphology and other things, but not for stormwater network. In
So
stormwater
my next,
network, we can take only the blockages. So if the inlets or pipes are blocked by 10%, 20%, we can specify those pipes and model that, how that model will affect.
so my next question was based on this only, that can we adopt this same methodology on the catchment basis also? Like we have the river networks, tributaries are joining.
Right.
So that same
Yes,
can be
yes.
replicated to that study using the same software, or we have to go to that UV, that you flow sediment.
No, it is same the sum. So this as of now, I didn't have any river data, so I just modeled stormwater network. But say suppose this is Yamuna River, so we can, if I have the river cross sections for this, I can easily put the flow data or 1D 2D model, and then it is a 1D 2D as well as the stormwater network. So that is why it is called as integrated catchment model. Means we can have the river network as well as this whatever is the stormwater network in one model itself. It is not something separate. So it's all part of one network.
Okay, sir.
Any other question? In reality, there will be some sedimentation with this stormwater, which will be entering into the network. But because of the velocity, certain velocity within the system, it will be carried away. But if the particles are larger, then they will settle down the moment there is a less velocity to carry those particles. So that's why in some regions we need to have some maintenance regime on a periodical basis to understand which areas will be more affected by those sedimentation over time. Because that will reduce the carrying capacity of the system. That's why the another aspect of ongoing maintenance is very, very important. But with time, normally the operators or the managers, they know which area will be more affected over time, and they develop periodical maintenance regime to take into consideration that aspect. So I will request Dr. Sharma to thank Rishi for his.
Maybe I'll just show you just for 2 more minutes. Sir. I'll show you maybe in Tuflo's website, which might be useful for others in terms of just to go through. So this is a Tuflo's website if you want to go through. One good thing is if you want to just learn some tutorials and all. So there's if you go to Tuf Library Wiki and just let it. While it loads, this is the QDM manual, Queensland Urban Drainage Manual. I sent to professors, so maybe they can share this manual. It's freely available and it has good understanding about different contexts of details of design for Australia, but some modeling scenarios or different things can be understood here. So you can go through this if it's okay. And okay, I'll show you about Tuflo Wiki. So once you go to Tuflo Wiki, I'll just open it. So these are the examples which you have, 2D base model topographic updates. So all these models, you don't have to have any license. It will run license free. So you can say, suppose now what we did, the integrated urban drainage, this is a model which is freely available. You can use that for learning purposes. And apart from that, there's example models. So there are around 140 standalone examples models, which you can use for learning purposes. And as I said, there's always a demo version where you can run any of your models within some small, it should be a smaller model. Within some specified time frame, it can run. So that is all about this. And Tuflo also, they do a lot of modeling videos, publications, benchmarkings. You can go through these manuals as well. Maybe this is the pricing page. This is where what we discuss is Stifler Classic or HPC. That is a fixed grade approach, which is river modeling or urban stormwater network. As of now, for INR we have the price list, as well as for INR we can use it, and this is for FE. FE is for the environmental approach for sedimentation, water quality, and other aspects. So so this is all about this. I think you can go through this, and that's all. So I just wanted to show this. That is all from my side. If you have any training you want, I can share that as well. Yes. Yes, sir. I think that's all from my side. Yeah.
Okay, thank you, Rishi, for nice lecture.
Yes, sir.
Okay, we can contact you later, okay, in future, and participants also can
Yes, sir.
contact you regarding this
Thank
any
you very
doubt,
much. Yes, sir. Thank you.
software and
Yes,
other.
sir. Sure.